tonight, tomorrow morning. Because the deadline is midnight. Yes. Someone was asking on the anonymous chat whether in this part of the course there is a course material, like something you had in the first week. I don't have that, so I think it's enough. The reference that I put for the book or the classes or the slides, the videos, I hope it's fine. Since it's the first time I'm teaching the actual classes, I don't have like material from the previous one. That's why I didn't write. But probably next year students will have that. Sorry about that. But I think it's enough to follow the classes. And like all the materials are like if you look at the book that I put the references in the slide, it's like kind of a course material because I'm not inventing stuff. I follow the book. I hope it's fine. Yeah, I was talking up with a friend about what I teach. So I was like, yeah, but can you explain me better? And like, so he said, so essentially what you do is vintage neural network. And I think it's kind of accurate because we're not doing like neural network like actual, kind of doing like the old stuff that led to this. So I thought it was a fun joke. Also, last time I made a mistake, did someone spot it? Was in the slides, but now it's corrected, so it's not there anymore. If you do, you get 3 points. So that's why I give you 1 second to think about it, and then I'm gonna tell you what mistake if you do. No. Yeah, I'm just gonna tell you it was a stupid mistake, but still. Last time I said that in a BAM, the activation function is the sign function. The definition of the sign function is this: 1, 0, minus 1, 1 if x is positive, 0 if x is equal to 0. Some people don't define it with 0, it's also possible. And minus 1 if x is negative. This is the sign function. And it's the activation function in the BAM network. And last time I told you, yes, this is equal to Heaviside step function of theta equal to 0. And that is false. Because the Heaviside step function is defined like this. They're not the same thing. And I thought they were. But this is the activation function we use in the BAM. And today we're going to see that we can change the activation function and see what happens. So, yeah. Of course, you can go from one to the other. I don't know how. I don't know. Effects. For example, effects different from 0. You can do this. H0 of x is equal to 1 plus the sine of x divided by 2. Voila. Is this really important? No. And you can put, I don't know, you can put effects. You can just put it equal to 1. So they glue together. Sorry. Okay. But not really important for all this. But it kind of is, in the sense that having the set function like this, you remember that we had 0 when we were removing the threshold, right? We were like creating this extra input edge containing minus theta as weight. So we had all the at the nodes, especially in perceptrons, we had 0 like threshold, and this led to outputs that were either 1 or 0, like the functions that we were obtaining. In the mechano-fixed units, the inputs was also 0 and 1, and the outputs was 0, 1. And in perceptrons, the input was whatever, we use R2, I think, but the output was 0 and 1, and it was kind of due to the fact that the activation function was like this. Now, if we use the sign function as an activation function, this means that somehow, if we don't fall in this case, the output vectors after an iteration are actually ones and minus ones. So that is a difference. And we're gonna deal with it today. And we can call them sign vectors if you want. A sign vector so that belongs to the power of n. There is a few things we could say about sign vectors. I don't know if saying it now or when I use it. So I have to talk about orthogonality. Let's see it now. So in general, if I have two vectors in Rn, V and W in Rn, they're said to be orthogonal if and only if V scalar W is equal to 0. When I have two sign vectors, so let's try to do the same. So those are vectors that are just like this: 1, minus 1, 1. They have ones and minus 1. The only numbers that you can put in are those. But what's the issue is that if I have two sign vectors V and W that belong to this, and I want to say they are orthogonal, there is a problem with n. So if n is odd, if n is even, I can be like they can be orthogonal. But if n, everything is fine. But if n is odd, I can't. Because imagine that I have these two vectors, okay, 1, minus 1, and 1. This is my V, and this is my W. I try to make it orthogonal to this one, so I don't know, I put minus 1 here, so I don't know. I put minus 1 here, I can put also ones. Whatever I put here, the results will never be 0 when I do the scalar product. I always have an extra 1 or minus 1, that's the point. That's why it doesn't work. So we can talk about orthogonality if n is even. This is not a big deal, but we will use it later, so that's why I was. Of course, if n is odd, you can talk about, like, I don't know, define your own concept of orthogonality. You say they're quasi-orthogonal. Like, for example, the scalar product is 1 or minus 1. It can be 2, 3, whatever. But if it's 1 or minus 1, it's the closest thing to being orthogonal. So there is, I think, ways of dealing with this. Yes. So, yeah, I'm actually kind of writing like an outreach paper on this topic. So at some point, it will come out if you're interested in sign vectors and related things. I don't know. This is all we're doing. Let's do with the slides because I forgot. What's after? Let's see. Yes, okay, we don't care. Yeah, so I was telling you last time about bidirectional associative memories. What are those things? I know also another. Okay, we were saying that the sign function is the activation functions for these machines. So a property of the sign function that we will need after is this. I have the sign of a vector x, and I multiply x by a constant k belonging to the real numbers, k positive, strictly positive, which is equal. The sign doesn't change if I multiply by a positive function. Like if I have a vector, if I have like a number, and I multiply it by a positive constant, the sign of the number doesn't change. So I don't care about it. This is true. I'm gonna use it later. So what the hell is going on? Yes. So those machines work in this way. You have one layer of axis. Can I cancel this? Everything. You have the video. You start it. So what do these machines do is you have two layers. You have x that belong to the first one and y that belongs to the second one. This machine computes always in 2 steps. We call one iteration the set of the 2 steps. The first step is called the forward step that goes from the x's to the y's, and the feedback step goes from the y's to the x's. So that's why it's called bidirectional, because the arrows, it's not drawn like, sorry for the drawing, it's not my, but like you put like actually double edge arrows, because you use the same streets to go and to come back in some sense, okay? How does this machine compute? So there is probably the formula here. Yes, so all the information about the, let me write an example here so it's easier to follow. This thing is fully connected, so there is arrows everywhere that connect everyone with everyone else. Nodes are also called units sometimes. Okay, this is X1, X3, X3, Y1, and Y2. So there is this matrix that tells you the weights, contains all the information about the weights. So for example, in this case, this is W11, this is W12. The weight tells you from where to where it goes. And the way the weights are stored is in the picture. So for example, in this case, the weight, or it's also called the transition, which I didn't say that last time. Like you put W11, W21, W31, W12, W22, W32. This is it. It computes in this way. You're given a first vector that we call x0. It's called the key, and I give it from the left side. I could give also like a starting key from the right side. Actually, it's the same. It's called bidirectional for a reason. We choose one side where you start, and you give the first vector. The way you compute is that you obtain y0. You start with x0, okay? You do the first forward step. So you obtain y0 as the way you can do the multiplication. It's just one, because the matrix is not squared necessarily. Like the first layer has dimension n, and the second layer has dimension k, that are not necessarily equal. So you do y, and you do activation function of x0, x0. Okay, because this is a line vector, n-dimensional vector, x0, and this is a matrix that is as in general n lines and k column. Because n is 3 in this case and k is 2. Note that the sign function gives us, no matter what was x0, no matter what the weights were, gives us what I call the sign vector. Since it's computing the sign, let's exclude the case in which x is equal to this case won't happen. So what you obtain from this is a sign vector. What I'm saying is that all the couples that you obtain from these iterations, the couples x, y, we will put the index of the iteration here, belong to sign vectors like this. N times 1, like this. No matter what the weights are, you will obtain vectors like that. That is different from what you were doing before, and this is due to the fact that we use the sign function as an activation. So, what was the question? Okay, so you can compute. You can keep doing that. In this way, you obtain y0. So you have the first couple x0, y0. Then you compute your x1. The way you do it is that you do the multiplication that you can do. So you put the transpose and you put y on the other side. In the exercise of this week, you are going to actually do those computations. So you can see that there is no other way of multiplying w and y if they have different dimensions than that, other than that. But the formula tells us that x1 transpose is equal to the sine of w y0 transpose. You obtain your x1, and then you obtain your y1 as before. Etc. That's how it computes. In general, you say that I'll write it from the index. So you obtain a sequence of couples. Each iteration gives you a couple, and each iteration is composed of two steps, one forward and one feedback. And the couples are related in the following way. So y is related to sine xi w. So y, when you go from y, when you do the feedback, basically, no, sorry, when you do the forward, you have the same index, but when you do the feedback, you have one more index. You see that xi, so I don't know if I have to write this, but yeah, the relation between the iteration is the following: yi is equal to the sine of xi w, and xi plus 1 transpose is equal to the sine of y w, sorry, yi. That's how it works. With this, you can compute iterations of a bidirectional network. In the activation function is the sine. All those couples are actually sine vectors, as I just said. Note that this way of obtaining like all the new y, like all the y vector, is that yi is a vector, a k vector at iteration I. Sorry. The index I is not the coordinate of the vector, is the iteration. So for example, those are m iterations. Those are couples of vectors. In each couple, the first is an n-dimensional vector, and the second one is a k-dimensional vector. Okay? The index here is just the iteration. In this way, we start from, let's find a picture. No. Okay, let's forget. No, what did I do? Damn. Yes. Yes, that's what I like. Okay, so we start from a vector of x's, and we obtain a vector of y's. In some sense, we are updating the y's, we say simultaneously, because all the information to update is contained in this matrix, and we multiply it by the x's to obtain the y's, for example, in the forward step. So we call this a simultaneous update. So we use all the information of the matrix to update everything. It's kind of like the case as we saw in the perceptron, but with many nodes. So instead of like saying, oh, I update this guy using those two, and I find a new y, here I'm just doing all of them together with the matrix. This is called simultaneous update of a bidirectional associative memory. It is not supposed to be always like that. I can also choose to, instead of using the matrix all together as a block, I can choose, I pick one node, y1, and I update just that. How do I do that? I use the information in the matrix, but I update just here. So I can do what is called an asynchronous update of the network, even in a machine like that. The information about how to update the node, I will find it in the matrix. For example, in this case, I can update just y1, and I say that the new y1 is the sine of x1 w11, as we were doing in perceptrons. I mean, it's just that the activation function is different, but it's the same thing. x2 w1 2 1 plus x3 w31, and I update just that. I choose one randomly. We're gonna see that optic networks do that actually. This is called simultaneous update with the whole matrix, but if you choose a node and you update just that, you can do it also in the other direction. So I can choose to update just x2. I take the information of all the others that I go to x2 and I update x2. I don't know. I choose to update randomly to update x2, and I say that x2 is the sign, the new value of x2 is the sign of y1 w21, suppose, plus y2 w22. It's a choice to see how we update this function. That's kind of why bidirectional and associative networks are the transitions from what we saw before. That was simultaneous updates. So like also in classic neural networks, like you have layers and you update each layer. You go in one direction and you update everyone with the matrix. In this case, we can do both. We can either update one layer at a time with this like transition equations like this. This is simultaneous because I'm using the whole matrix, and I update all the y's, all the x's at the same time. And in this case, I can also just take the network and say, I can write an algorithm that says, I pick one node and I update that using the weights. The weights are contained here, so I can find information and I just update one. That's the idea. So what we were talking about last time. Okay, yes. I think I mentioned that. I mean, it's not shocking to talk about convergence. Like, what do these networks do? Imagine that I give you a bidirectional associative network like that. I give you a key, so a starting vector, and I tell you just iterate. For example, with the simultaneous update. So update like normally with the you apply the matrix and you apply these formulas. You start with the y0, you multiply, and you know. The question that might come is like, what happens like on the long term? Like if I keep updating, does something happen, or does this thing converge to something? So the question is, do I find a couple that I can call? Let's put it here. So if I find a couple x tilde, y tilde, I don't know if it's a tilde. Does it exist a couple such that my network jumps from one state to the other, okay? And I obtain a sequence of, I start with x0, y0, then I go to x1, y1, then I go to another x2 and y2. But at some point, I always find the same couple. Like my network changes its values, but does at some point jumps always between the same two? This is the question. I brought an arcane, but actually it's -1, 1, n times -1, 1. K, if the activation function is the sum. Later we're gonna see that we can change the activation function. That's why it's arcane. But yeah, so what does it mean having a fixed point? Means that this is how my machine iterates. Means that when I go from this to this, I use this equation. But then when I come back, I want to jump to the same one. So I want this to be equal to xi. If this is true, then I'm jumping always between the same two because I obtain xi. But when I apply the iteration to xi, I obtain yi, etc. Let's write it with the tilde. So a fixed point or a stable state dynamic consistency is also called an attractor. So something that when you end there, you never come out. There is these two concepts like an attractor and a repulsor. A repulsor is like when you have the pendulums and you take the pendulums and you put it on the top, it will always run away. Whereas the lower equilibrium is like an attractor because if you're close, you stay around there. Whereas the upper, if I take the pendulums and I put it on the top, it will always like run away from that. So that top state is called a repulsor. and the other one is called an attractor. So what we're looking for in these networks are actually attractors, because when we fall in a stable state, the network will always jump between those two vectors, so we will stay in the stable state. And by state, I mean the couple. So it's true that the network jumps between two vectors, but they're always the same two vectors. So my stable state is a couple of vectors. It's a couple of vectors x tilde defined by a couple of vectors defined like this. Y tilde is the sign of x tilde w, and it's equal to the sign of the. So the three equations characterize my stable state. So I start with x. If I start with x tilde, I obtain y tilde. But if I start with y tilde, I obtain x tilde. So I will always jump. So if I start with a stable state, I basically won't move from this couple. Like all my sequence, like the iteration of my network will give me a sequence of couples of vectors, and they will all be the same. The first one is this one. So there is a question like, given a couple, how do I find a network such that the couple is stable state for the network? So I know this couple of vectors, and I want to know the W, because if I have the W, and I said that the activation function is the sign, I have the network. Because the size of those vectors will also determine the number of nodes that I have on the first layer and on the second layer. Is that clear, the question? Are there any questions so far online? Are there any people online?
There are.
This one can excuse me. So, yes. So, the answer to this question is this. Let's find out. First, I just said that this is an n-dimensional vector and this is a k-dimensional vector with -1, 1. Let's write the matrix W. So this is a matrix that does the job. Of course, there is more. But it's not that there is one-to-one correspondence between the couple and the matrix such that that couple is fixed point. But this gives you a solution, gives you a network that replies to your question, my question. So I define the transition matrix as this, X tilde transposed Y tilde. And I said this solves the problem. We have to prove why it's true. So we have to prove that even this is a stable state for this. Okay. So first of all, these are the right size to be a network that takes input n-dimensional and outputs like k-dimensional and vice versa. Because if I take X transpose, this is a column of n, and this is a row of k. The result is a matrix that is n times k. Right? Because I do this, and I obtain a matrix that is this. N is k. Right? Well, now we have to prove that if I start from X tilde, I end up in Y tilde. And if I start with Y tilde, I end up in X tilde. So I'm jumping between those two using this matrix W. Wait. So I start with x tilde. And I'm saying I do the sign of x. That's how it iterates, by the way. So if I start from x tilde, I'm supposed to do this. X tilde w, but w was x tilde transposed y tilde for w. But if I look at this is an n-dimensional vector, an n-dimensional row and column. So this is like the scalar product between x tilde and itself. So this is the squared norm of x tilde. But the norm is usually positive. So this is a positive number. And I told you before that if I have a positive number in a sign function, I just don't care because the sign will not change. When I apply a sign function to a vector, because the sign is like gives you the sign of a number, but if I have a vector, you just do it for every comma. So if I want to do the sign, I don't know, maybe I shouldn't say it. Maybe it's clear. But if I have -1, 3, -7, I obtain a vector. 1, -1, 1, 7, 6, 1. Okay. I do it for component, so this is all about. It's okay. This is the sign of y tilde. But I told you that those vectors are already sign vectors. So if I do the sign of a vector that is already -1s and 1s, it's just itself. If I do the other way around, so if I use the other second equation of computation of these machines, I do W, and I start with W tilde transposed. And my hope is to obtain x tilde transpose. So I'm coming from the right layer and I go back to the first layer and I hope to end up in the same point. So I use the definition of W again, which is x tilde transpose y tilde. Why did I use all those tildes? It's just lots of time. Yes, but this is the norm again. This is W. And this is the norm, so I have to tilde transpose times. This is a number that multiplies a vector. I don't care, this is a positive number, so won't change the sign. But this is already a sign vector. So I'm assuming that the couple x tilde, y tilde, maybe I should change that in the slides. Belongs to the couple -1, 1 at the time. And okay. And this is equal to x tilde transpose because it was already a sign vector. So I proved that this was a fixed point. If I define the matrix in this way, I'm sure that this vector, this couple of vectors is a stable state. So the question now is, what if I have many? Like, imagine that I have many points, many couples that I want to be fixed for a network. What is a network? How do I find a network? Because the definition of W this way gives me it for just one. What happens if I want many of those? So There is a new question. Probably I made a slide. Question, yes. What happens if I want many points to be fixed? So I have many couples. I have M, and I want all of them to be stable state for a network. How do I find the network? Can I done so? Easy than on the slide. Let's leave this here. So it's this one. Okay, is there a question? So I have many couples, X tilde one, X tilde two, sorry, Y tilde one. So here the number is not the iteration. The number is which couple. And I put tilde because I want it to be stable. So I will call always tilde, like with this squiggle, always stable state. But yeah, so I have all these couples. I want all of them to be stable states. How do I find W? So to have an easy solution to this problem, what am I going to do is that I'm going to assume something on those couples. First of all, that I want them to be pairwise orthogonal. Hypothesis. But before explaining what this is, since I wrote this implies a second hypothesis. This is hypothesis one, this is hypothesis two. Is that N and K need to be both even. What do I call pairwise orthogonalities between the couple? Whenever I take I and J in one M, I have an I different from J. I have that X tilde I scalar X tilde J 0 and Y. Not a crazy idea, but like Y time pairwise orthogonal. The x's are orthogonal to the x's and the y's are orthogonal to the y's. Whenever I pick two like this, they're orthogonal. Whenever I pick two like this, just the x's. They're orthogonal. Is that okay? We're not doing crazy stuff. So under those assumptions, I can find a matrix of a network such that all those are fixed points. And it's just the same idea as before, but iterated. So it's not work done. Let's finish this and then we take a break. So what I want is that, let's put it here. I want to prove, to find W such that all those y tilde I It's the same like condition of being a fixed point. People don't see this. And the other thing holds. So x with the I transpose is equal to the sine of W y with the I. So is that being each of those for all I? That goes from 1 to m. I want all of them to be fixed points. So what do? I define, yeah, we'll cancel this. So what do is that I define W as the same as we did before we did what? Yes. X tilde 1 transpose y tilde 1. This was the definition of W we had before, but this is just for one, for the first couple. And then I just sum x tilde 2. This is a matrix that is n times k. I do it for every one of those. Transpose y tilde 2 plus blah blah plus x tilde m transpose y tilde. All those blocks are n times k matrix. If I sum n times k matrix, I obtain an n times k matrix. So these are the correct size. We have to prove that this does the job, so that those couples that I just cancelled are fixed points for this one. Okay. Let's just fix one couple so we don't go crazy. Let's consider a couple xi, yi. We try to prove, let me count this. This is what we want to prove. I put this first one and second two. We have to prove the first one. So I start with x tilde I. Do I end up with y tilde I for all I? So I do this as here. W. Then I just put in the definition of W. So as here. X tilde I, and then x tilde 1 transpose y tilde 1 plus etc. plus. But now, the things were pairwise orthogonal. So, I mean, the scalar product between, for example, xi and xj, x to the I, scalar x to the j, this is actually equal to x to the I, x to the j. Do you agree? Because this is line, this is row, and this is column, gives me the scalar product. So if I took away the scalar product and I put t, is right. But I was saying that all these are equal to 0 if x is different than 1. This was my hypothesis. So this means that between all these terms, this part would be 0 and would be equal to the square norm of xi, just in the case in which I and j are equal. Okay. So in other words, like this is just equal to the sine of x tilde I, x tilde I transpose y I. Because all the other terms are 0, but now it's as before. So this is the norm, the squared norm of xi tilde square. This is a real number. The sign doesn't care about a positive number, so take it away. Yi is a sorry, this is so. Do I have to do all this? Yes, as y tilde I. But it was already a sign vector, so obtain y tilde I. So I started from this fixed point, and this is true for all i's. I started from x tilde I, and I end up in y tilde I, so this is true. We proved 1. We can prove 2. That's all 2. Let us suppose we start from x tilde I, sorry, for y tilde I. It's the same thing. So I put the definition of W, the couples x tilde 1, x, y. Tilde 1. I have those two couples that I want them to be stable states. And I say that they belong to the axis belongs to 2. What? What does it mean? That my network is something like this. And I say that x tilde 1 is equal to 1, 1. I mean, those vectors are sign vectors because you have the sign function, but you can give as a key, so the first one you give to the network, something that is not minus 1s and 1. The problem is that as the first iteration, you will obtain something that has minus 1s and 1s. So something that is not minus 1s and 1s can be a starting point, but cannot be a fixed point, because then I have to come back. And when I come back, I will also use the sign function. So I will never come back to something that is, I don't know, 2 or 3, because my sign function gives me 1s and minus 1. So that's why we assume that all of these belong to minus 1. I give you these vectors. You can verify by your own that pair 1 is orthogonal. So if I define W as I just said, do I do all the steps? No. What I obtain is the sum of these two matrices. So this is given by the first couple, and the second couple gives me this. So the result of this stage is this matrix. And you can verify that those points are fixed points for this. So yeah, let's do that. This is true for I equal to 1 and 2. This means that I can put those weights on this. Well, so those numbers are actually those that are supposed to be on this. This is, for example, 2. Or on all these bidirectional arrows, you're supposed to put those weights on this. Right. The matrix gives you the network. Yeah. Do you want me to compute one of those, or do you agree that those are fixed points for this matrix? Very far. For example, when you apply x to the 1, so you start with this. You obtain, putting 1, 1 in that matrix, you obtain the sign of the vector 2, 2, 2, 2. That is 1, 1, 1, that is y tilde 1, so etc. So this condition is verified. Again, the exists condition for the first couple and then both condition for 2. So is that all right? Yeah, okay, what we did until now is given couples of vectors, find a way, or find given one couple of vectors, find a network that has that as fixed point. But doesn't tell you the inverse. Like if I give you whatever network, how does it converge to a fixed point? Like that, how do I even, like, it's not that all the weights matrix are like this. So like, yeah, how given a random network, how do I find the stable state? Does it even converge to a stable state? That's the other question. Because for now I was starting from the stable state. If I start from the network, if the exercise gives you the network, how do you find the stable state? You can iterate, given a key, iterate, and see whether it converges or not. But can we be reassured that this thing converges or not? So to talk about convergence of a BAM, either with asynchronous, either with synchronous updates, because so far this is a synchronous updates. We apply the matrix to all the nodes, but convergence should hold also for random updates, like for asynchronous updates. But let's go step by step. We have to talk about energy function to prove that result. So this is really important because it comes out also with optic network. So that's why. Let me cancel the example. We have to talk about energy. So we start again from 0. So imagine that we are given a t at 0 belonging to -1, 1 at the power of n. I compute the first step. So this y0 is equal to sine of x0. It was forward step to go on the other side. Now to go back to xy, imagine that it's not a stable state, so I continue. Come back to something that is potentially different, so that is x1 transpose is given by the sign of w y0 transpose. So I got this thing. This is the feedback step. So I'm taking all the information from the weights in y, sorry, the nodes in y, then I get the weights, and I compute, update all my axes in the first layer. The weight matrix is not supposed to be necessarily with ones and -1s. You see that before that the matrix had 2s and 0s, whatever. The vectors are, since the activation function is the sign function, the vectors are in -1s and 1s, the axes and the 1s. So this thing is not a sign vector necessarily, this multiplication. And then I compute the sign of it. So whatever is coming from the y layer and the weights, I call this thing excitation. A vector E transpose is equal to W y. There was a mistake in the book, by the way. They were missing the transpose at some point. So if you look at the book in this proof, there is a cross. So if the couple x0, y0, imagine that I started from something that is already a stable state, okay? Is stable. It means that when I came back to x1t, this was equal to x0t. So I started, I went on this side, I came back and I came back to the same thing. So this is the definition of like being here. Stable state. So what does it mean that using the excitation that x0 transpose is equal to the sign also this of E transpose. The sign compute switch and sign and transpose commute. So I can do this actually. Yeah, I think it's that. Because I'm doing it for each coordinate, so I don't care about the transpose. So what does it mean is that x0 is equal to the sign of the excitation. So, yeah. This excitation vector is excitation from the right to the left of my vector. I don't know if I need the drawing, but yeah. Let me draw something. Consider minus 1, 1 at the power of 2, because I have a two-dimensional blackboard. Okay, this is R2, but this is contained in this. So this set contains just 4 points. Do you agree? So if imagine this is my x0. Yeah. So this is the equation that I just created here. So we have to understand the like. Imagine this is my x0, and I consider the excitation vector, not the sign of the excitation vector, just the excitation vector. Okay. Vectors E chosen in this square are close to x0. When I compute their sign value, x0 is a sign vector, okay? If I take E here, for example, and then I compute the sign is equal to x0. In some sense, like whatever excitation vector that is not a sign vector I chose that is close enough to x0, so that is in the same quadrant, when I compute its sign, it will be x0. Like I will not obtain the same thing if I take E here. If I take this vector here and I compute its sign, then I do sign of E, I will obtain this. But basically, whenever I'm close enough to x0, I will fall on that. Whatever like small variation I do in E. So What does it mean close enough? Talking about E and X0. Means that the scalar product is big. So if two vectors are close, the angle is small. Imagine that this is X0 and this is E. The angle is small, but the scalar product is bigger, like it's maximized when they're parallel, okay? So if I write X0 and E transposed, I'm doing the scalar product between X0 and E. So whenever I'm close to a stable point, this scalar product is maximized because I'm close to X0. Because I was saying that X0 is a stable point when this is equal, right? So whenever I'm close, this scalar product is maximized, this quantity. And if I put a minus to this, I minimize it. And so minus X0 excitation T, we call this the energy. That's how we introduce the energy. So energy is mean. This is just an intuitive definition, like it actually needs to be proven. But intuitively, what happens is that in stable states, this product is maximized, so the minus that product is minimized. So there is this intuition that stable states are local minima for the energy function. Let's write the energy function in a more nice way. We talk about energy in a couple, so energy of a state. So a couple of vectors belonging to the first and second linear. So we call energy of X, for example, X0 or 0 minus a half. Then let's talk later about this half, but minus a half of X0 W, oh sorry, excitation, but yeah, that was W X0 Y0 transpose. I think it's not sure. Yes, it's not, because you cannot find it. This was excitation. I remember that I defined this excitation transpose. Before I defined the excitation as this. Yes. Excitation transpose was equal to W Y0 transpose. So this is excitation transpose. It is calculated in X0, Y0, but in general, you can calculate it in whatever couple of vectors at stage, at iteration I. Minus a half. The minus is important because we want to minimize the energy. Yeah. So main things. This constant doesn't matter because it's just a constant. It's not that the minima will change. It's just a positive constant. It's a half. It has some kind of like historical relation to physics and stuff. I don't know if you have ever seen like the kinetic energy tensor or this kind of like energy things. This a half here all the time. But yeah, it's just a constant. We don't care. But also, if X and Y are the same size, This is like using, I don't know if you've ever seen quadratic forms. This is like using W as a quadratic form. I don't know. For example, a simple example of quadratic form is the one associated to the Euclidean scalar product. So if you take the identity matrix, for example, 3-dimensional, so you take one. Quadratic forms, they have to be square, 3-dimension. If you take, you do this, put a vector on one side and on the other, if you put the same x, I think, that's false, you obtain the scalar product. You do this product. Do this product with a vector x, you obtain. So that's an idea that we use metrics to compute norms. And all this is a number, it's a scalar. So it's like some kind of index. Since I told you before that intuitively, what happens is that the energy needs to be minimized. The energy is a constant in this system such that tells us whether we're approaching a stable state or not. And we talk about local minima because we don't know whether there is one or more. And wherever we start, we don't know in which one we will end up. In off-field network, we're going to see this in a more detailed way. And also we're going to prove convergence. Yes, this is one thing. Before talking about off-field networks, we need to do something else. So the energy is a scalar that tells us whether we're approaching a stable state or not. Whenever it becomes smaller and smaller, at some point we will end up in a stable state, and it's a constant. We have to do something that we did already for perceptrons now, but let's do it with this. So this is the energy function of a band with activation function, the sign. But we can change the activation function. So we can put threshold to the, so okay, let's make an example, probably it's better. So I have x1, xn, in the first layer, and in the second layer I have y1, yk. Imagine that I don't have the sign function anymore. And imagine that I have, let me use the same notation because otherwise it's gonna be messed up. Yes. Imagine that we have a threshold, so a heaviside step function instead of a sign function. And heaviside step functions will be with thresholds different for each node. So I put a different threshold here. So I call this theta 1, theta n. And I call theta the n vector of thresholds of the first layer. And the second layer, I call it phi, and I put phi1, pk. Meaning that now the activation functions are a heaviside theta I for the node I, or heaviside pj, I don't know, for the second layer. And we do it as before the computation. So we have the weights again, same thing as before, okay? How? So also now the vectors, since the activation function is this, and the activation functions of x, yes. Yes. No. What? Because when you take the y's, then you apply the thresholds, and you take the x's. When you this you apply, whereas with this you apply the x. But anyways, all this is to say that heaviside step function is either 1 or 0. So whenever we change the activation functions, all our vectors x's and y's, would belong to 0, 1 instead of minus 1 and 1. Yes. So, how did we deal before with this heaviside crap? What we did, I don't know if you remember, is that we added an extra node. So instead of having this network, etc., we have the same one, x1, xn. Okay, my scope here is to define what is an extended BAM with the different activation function, but also to say what's the energy for this thing, because it will be different. So what we did was to add an extra node. You remember that? These were the nodes, and then we have this node that has 1 as value, and as all the weights between those are the weights in the W, because we said that the weights that go from this to this are defined by W. And I add an extra node here as well. So whenever I connect this to any other of those, that have, this is Y1, YK, and this is P1, PK, theta 1, theta n. Those were the thresholds. Instead of putting the thresholds, I put the threshold to 0. And I put minus phi 1, minus phi n. To put the thresholds to 0, we had adapted as this thing. We put an extra node, and we put the threshold as a weight. We do the same for the other way around. So whenever I connect this to one of those, I put minus this. I put 1 as input here, and I put minus the threshold on the weight. And to connect those two, I just put 0. We had done this for perceptrons, just with one node. Imagine that you have one node and you have a threshold, 1 unit with a threshold. We were removing the threshold and putting that as a weight. I don't know if we have. So, what does it give us? Extended input space and extended input space, because now we have 2. Instead of having x that was x1, xn, we have a vector that is extended. So we have I call it big X, and I put X in the first coordinates, all the coordinates of X in the first place, and then I put 1. This was the extended input space. And I can put Y, the same thing, I call it big Y, that is tiny y, 1. Yeah. Now I have so this was a network with n and n. This has n plus 1 and k plus 1 now. Those belong to R, and those belong to RK. How do I compute the energy of these things? So let's try to write. So imagine I didn't know that I added these extra ones. Imagine that I treat it as a network that is n plus 1 times k plus 1, okay? Imagine I didn't know. So the energy, as I defined it before, imagine that I consider x, big xi, big yi, that are a couple. For this network, big network, I didn't know that those were ones. Imagine I do that, then I use the definition I did before. So the energy calculated at yi, it's minus a half xi w yi transpose. The definition I gave before. But now those are, so let's call it W prime. But now those are the extended input vectors, and this W has extra weights, more than the weights of W. W is the one just up till here, and I have added these extra weights. So oh God, okay. Let's finish this part and move on. Okay. So we have to think about what this W prime is, like this W extended with all these extra ones. And then if it's clear that I added those on these edges, but I should do those also with those ones. Probably I should write it. But this one, this one. I do it also with the thresholds for this. So this one I added a new node, so I have to connect it to all the rest. Instead of putting theta 1, I put 0. This I put 0 on this edge. And this I put minus theta 1, minus theta k. No, minus theta n. Because those are n. Imagine this was my W. My W is n rows times k columns. W11, Wn1, Wn k, W1k. I added extra weights. So my W prime is a matrix that contains W inside, but that also those as entries. Imagine that I didn't know that those were introduced by myself artificially. What is the weight matrix of W? So, first of all, since this is a network with n plus 1 and k plus 1, this W prime should be k plus 1 columns and n plus 1 rows. So easy, I start with this, I refill all those with W, so I have n and k. I have n and k. This tells me how to go from the extra 1 to the extra 1, and I set it 0. I put 0 here. Now I have two vectors of weights that I added. These are without the minuses, but I added the threshold with the minus. If you remember, we added this. Yeah, you remember. Wi, xi, minus theta. That was the sign that was checked. 0. Theta was on the other side. This was second week. Basically this, but for every node. That's why we have minus the threshold. So what do I put here? What do I put here? Minus theta vector transpose. And this is minus 0. Because phi is rk, and here I just have space for k, and this is n, so I have space for n threshold. And this is the weight matrix of the extended network. Seems chaotic. I'm gonna do an example first thing next time. But it's just that try to generalize to deep down the fact of adding thresholds and removing them. So, but if my matrix is this, what the hell is the energy then? Good luck with that. How much time do we have?
5 minutes.
Madonna.
Maybe 6.
Gonna be fun. Okay. So let's write it down in the matrix then. So the energy of xi yi. I use the definition as before, even though now it's every side with threshold 0 and before it was sign. The difference is that now I have vectors with zeros and ones, and before I had minus ones and ones. But we defined the energy in the same way. Minus 1 xi w prime w what I transpose. Let's figure this out. So we put the definition of everybody. So minus a half xi is this, as all the coordinates of xi plus a coordinate equal to 1. It's rho, so I put it in rho. I 1. Now I put to w, that w prime, that is what I put before. So w minus phi minus theta transpose 0. Okay. And this is why I transpose. So this is this, but it's put as a column, so I put it like here. All the coordinates of y and a 1. This notation is just to say, okay, I don't care what's inside. I'm supposed to know what is going on. Let's keep it like this and we do this multiplication. So xi1. We do this multiplication, so we do this and this. Those are the right sizes actually. So I have a column vector. Do you agree? The first coordinate is what? And the second coordinate is what? W. This is transpose. Yes. As a column. W y I transpose minus theta transpose. This is the first part. That is n dimension. Plus theta n dimension. And this is just one number. What number is this? This and this. This is a scalar product of two vectors that are dimension k. Minus phi y I transpose plus 0. I don't care about the plus 0. So let's move on with life. So minus a half. And then I do again this times this and this times this. I have xi w y I transpose yeah, let's put parentheses maybe minus theta transpose. That is just the first, multiply the first. Yes, put another parenthesis minus this times this, so it's just minus p y I transpose. Okay. We can conclude kind of. We do all the parentheses, all the multiplication. This is on half x I w y I. Did I forget an no? I transpose. Same energy as before. The energy of the small network without extension. This is the equation we had before. With the tiny axis instead of the big axis. Then we have plus a half xi plus e y I. So, what? Plus two extra terms that are due the extra weights that I added to remove them as thresholds. So this is the energy of the extended network that depends as well on the weight. but depends as well on the energy of the small network before extending. Yeah, I think we're out of time. No.
Okay. And by the way, just so you know, this is really good that we have it in the here written, because in the book they don't do any of this. They just say evidently, and then they put this formula, and that's it.
So there is what I want to say is that this definition of energy relies on the fact that we don't have threshold. But there is a way, if we have thresholds on the nodes, to treat them, and they come out in the equation of the energy. And yeah, I think we stop here, and next time we do Hopfield networks in a more serious way, because I think I talked a little bit before about simultaneous and not simultaneous updates. And like one can consider a Hopfield network as a bidirectional, like the same concept holds, like the energy function and the not simultaneous updates can be used in the Hopfield model in the same way as they were used in a bidirectional network. So, yeah. This is already in the slides if you want to have a look, but yeah, we're gonna do this next week. Are there any questions?
Bye, guys.